Hi, welcome to my third video on calculus in the playlist of UPSC Maths Optional. So we are in the process of solving the problems based on limits. So we have solved the first 5 problems based on limits. So we have solved the first 5 problems and then we'll move on to the 6th problem, which is we need to find the limit of 1 plus 1 by n whole power n. So this is a very important limit. So we need to find the limit of 1 plus 1 by n whole power n. So if I substitute n is equal to 1 here, then I have 1 plus 1 by 1 power 1. So I'll have 2. So if I substitute n is equal to 2 here, then I have 1 plus 1 by 2 whole power 2. So 1 plus 1 by 2. 1 by 2 is 0.5. Then I have 1.5 whole power 2. So 1.5 whole power 2 is 2.25. So when I substitute n is equal to 1, I will have 2. If n is equal to 2, then I have 2.25. So you see that the value keeps on increasing from 2, 2.5, and then you substitute n is equal to 3 here. You check what the answer you will get, but you will surely get it will be greater than 2.25. So to find the limit for this function, first I am going to tell this sequence is an increasing sequence. So this function is an increasing function, which means if I substitute n is equal to 1, you will get a value which will be less than the second one. So I am going to show that the an is less than an plus 1. That is, the first term is less than the previous term is less than the next term. So an, I am going to show first, it is an increasing sequence. For an increasing sequence, I should say an is less than an plus 1. So after showing that this is an increasing function or sequence, I am going to show that this function is bounded above. It means it has a bound, which means it cannot exceed that value. First I am going to say it is increasing, and then I am going to show it is bounded. Now to show it is increasing, I am first taking this as an. So I am taking this as an. So an is 1 plus 1 by n whole power n. Now I need to show this an increasing sequence. To show an is increasing, since every sequence is a function, we can thought this. So an is increasing. So an is increasing, that is we need to show an plus 1. An will be less than an plus 1 will be greater than an, right? Because I have a1, a2, a3, a4. So if it is an increasing sequence, for example, I have 1, 2, 3, 4. So which means this value will be always greater than the previous value. So I have to prove an plus 1 will be greater than or equal to an. So for that, first, what is an? So an is 1 plus 1 by n whole power n. So I am going to expand this in binomial series. So we know that 1 plus x whole power n is 1 plus nx plus n into n minus 1 by 2 factorial x square plus n into n minus 1 n minus 2 by 3 factorial x cube, and it goes on. So what I am going to do here, I am going to expand. In place of x, I have 1 by n. So in place of x, I have 1 by n. So if I substitute here, I will have 1 plus nx. X is 1 by n. 1 plus nx plus n into n minus 1 by 2 factorial x square. So x square will be 1 by n whole square. Now this process goes on. Now I have this n and this n will get cancelled. So I have 1 plus n into n minus 1 by 2 factorial 1 by n square. So the next term will be n into n minus 1 n minus 2 by 3 factorial 1 by n cube, and goes on. So if I cancel the first n and second n, I will have here 1 plus I have n minus 1 by 2 factorial. So I can write n by n minus 1 as 1 minus 1 by n. So n minus 1 by n. Now here 1 by 3 factorial. So 1, I can write this as 1 minus 1 by n, 1 minus 2 by n. Now if I take n common here, this term will be 1 minus 1 by n. If I take n common here, this term will be 1 minus 2 by n. So this n will be n square. This n will be n. If I multiply here by n, it will be n cube. This n cube and this n cube will get cancelled. So you are left with 1 minus 1 by n, 1 minus 2 by n. And then this process goes on and on. Now this is an. I have found an. So what will be an plus 1? So I need to substitute n is equal to n plus 1. So I have 1 plus 1 plus 1 by 2 factorial. 1 by 2 factorial. This will be 1 minus 1 by n plus 1 plus 1 by 3 factorial, 1 minus 1 by n plus 1, 1 minus 2 by n plus 1, and goes on. Now we see that we see that 1 plus 1 by 1 plus n will be always less than 1 by n. Right? This is, if I substitute n is equal to 1 here, it will be 1 by 2 is less than 1. So 1 by 1 plus n will always be less than 1 by n. So this implies if I multiply here by minus, then I have minus of 1 plus 1 by 1 plus n will be greater than minus 1 by n. So if I multiply minus, the inequality will be reversed. So this means if I subtract some number, it will not alter. So if I add 1 both sides, this will be 1 minus 1 by n. So 1 minus 1 by n plus 1 will be greater than 1 minus 1 by n. So similarly 1 minus k by 1 plus n will be greater than 1 minus k by n. Now you see that this term will be greater than this term, because 1 minus k by 1 plus n will be greater than 1 minus k by n. So if I substitute k is equal to 1, 1 minus 1 by n plus 1 will be greater than 1 minus 1 by n. If I substitute k is equal to 2, then I have 1 minus 2 by n plus 1 will be greater than 1 minus 2 by n. So it follows that an plus 1 will be greater than or equal to an. So I have shown that this is an increasing function. Now next, an increasing function, and the starting value will be 2. The starting value will be 2. I don't know the ending value. So I'm going to find the ending value for this sequence. That means I'm going to find the bound for this sequence. 2. Now you see that now an. Now an is, an is 1 plus 1 by 2 factorial, which we found earlier, 1 minus 1 by n plus 1 by 3 factorial, 1 minus 1 by n, 1 minus 2 by n, and so on. So this I can write this as this will be less than or equal to, I am changing equal to sign to less than or equal to 1 plus 1 by 2 factorial. I am neglecting this term, 1 by 3 factorial up to, and goes on up to 1 by n factorial. So this term will be less than this term if I remove 1 minus 1 by n, 1 minus 1 by n, 1 minus 2 by n, and so on. Now this will be less than or equal to 1 plus 1 plus, now 2 factorial is 1 into 2, 3 factorial is 1 into 2 into 3 and n factorial is 1 into 2 into 3 into up to n, right? Now this will be equal to less than or equal to 1 plus 1 plus, now this is 2, so 1 by 2, this is 1 by 6, so 1 by, I am writing this as 2 into 2, I am writing the next term will be 2 into 2 into 2, and the next term will be 1 by 2 into 2 into 2 into 2. So this term will be 1 by 6. So this which will be less than 1 by 4. So 1 by 4 is less than 1 by 6. The next term will be 1 by 1 into 2 into 3 into 4. So 1 into 2 into 3 into 4 is 24. That will be less than, that will be greater than 1 by 2 into 2 into 2. So this term will be always less than the above term. So I can write this as 1 plus 1 plus 1 by 2, 1 by 2 square, 1 by 2 cube and to 1 by 2 power n minus 1. Now you can see that from here it is in the expansion of, it is a geometric series. So geometric series 1 plus x square plus x cube up to 1 x power n. So this will be 1 plus first term a, we know the geometric series converts to a minus r, 1 minus 1 by 2 power n by 1 minus 1 by 2. The geometric series converts to a into 1 minus r power n by 1 minus r. So this geometric series converts to a into 1 minus r power n by 1 minus r. So the a is first term, the first term is r, and r here is the difference of the first and second term, which is 1 by 2. So I have a 1 into 1 minus r power n. So r power n is 1 by 2 power n by 1 minus 1 by 2. So this will be less than 1 plus. So this will be 1 by 2. If I substitute, if I take this to numerator, it will become 2 by 1. 1 minus 1 by 2 power n. Now this will be less than 1 plus, multiplying here 2 minus 2 by 2 power n. So this will be less than 3 minus 2, I can write this as 1 by 2 power n minus 1. So I am writing, bringing 2 to the denominator, it will be 2 power n minus 1. So as n tends to infinity, as n grows bigger and bigger, this value become 0, because 1 by infinity will be 0, which means this is always less than 3. Right? Now the first value is 2. So if I substitute n is equal to 1, I have 2, and whatever you substitute, even if you substitute n is equal to 1 lakh, n is equal to 10 lakh, it will be 1. From the function we will have 1 by 1 plus 1 by 10 lakh whole power 10 lakh. This will be less than 3. So we have shown that this whatever may be n. So whatever may be n, for every n, this sequence, this function will always be less than 3. So what is the starting point? What is the starting value for this function? It is 2. So we have shown that 2 is the minimum lower bound and 3 is the upper bound. So the limit of this function will be lie between 2 and 3. So this implies limit lies between 2 and 3. So if you look on carefully, if you go through some basic concepts, we come to know this value it will be in between 2.666. It will goes on and on, which is an irrational number. So the limit for this will be 2, in between 2 and 3. So I am going to call that number as E. Call that as E. So therefore limit of 1 plus 1 by n will be e. So this is a very important question. So they asked us to show that the limit of 1 plus this n tends to infinity. If they haven't mentioned here, you should take that as n tends to infinity. So the limit for this will be 1 plus 1 by n is equal to 1 plus 1 by n whole power n. Whole power n will be e. So it's a very important question. So we have solved the 6th problem. Now we will solve the 7th problem. 7th problem is limit x tends to 0 a power x minus 1 by x. So 7th problem, I want to find the limit for this function. For this, first I am taking let a power x minus 1 is equal to y. So I am taking the numerator a power x minus 1 to be as y. Then we see that, and a power x will be 1 plus y. So if I take minus 1 to right hand side, it will become 1 plus y. Now if I want to find the x. Now numerator will become y. I need to find x in terms of y. So for that I am taking log on both sides. So if I take log on both sides, it will become log a power x is equal to log 1 plus y. So this will be equal to log a power x is x log a. So you remember that log a power anything is n times log a. So you can bring the power to multiply the power. So x times log a is equal to log of 1 plus y. So x log a is equal to log 1 plus y. So this means x is equal to log 1 plus y by log a. So I have found x. Now numerator will become y. So we have this will be equal to, now a power x minus 1 by x will be equal to, so a power x minus 1 is y. X will be changed to log 1 plus y by log a. So log a, right? Now I can write this as 1 by y log 1 plus y 1 by log a. I written this y as 1 by y. So 1 by y will be, if I take this to numerator, it will become y. So I written this y to be 1 by y in the denominator. So 1 by log a will be by log a, then as it is. Now I am taking log a to the numerator. So I have log a by 1 by y log 1 plus y, right? 1 by y plus log 1 by y. Now we need to find limit x tends to 0 a power x minus 1 by x. So this will be equal to limit, I have changed x to y. So this will be y tends to 0 because I am applying the change of limits here. This will be y tends to 0. This will be log a by 1 by y log 1 plus y. 1 by y log 1 plus y. Now I can write this as, change this to limit y tends to 0 log a by log 1 plus y whole power 1 by y, because log a power n is n log a. So I can write this as 1 by y log 1 plus y, which will be here. So I can write this to be this. Now I need to apply the limit. So as y tends to, there is no y term here, so I can take log a outside. Now here if I bring limit y tends to 0, 1 by log 1 plus y whole power 1 by y. Now this will be equal to log a. This will be, you look at the previous sum, 1 plus 1 by n, 1 plus n whole power 1 by n. This is e. So we have solved the previous sum, 1 plus n whole power 1 by n. Now we have y. So this will be 1 by log e. 1 by log e. So log e is 1 again. So this will be log a. So the limit for this is log a. So log a is the limit for this function. So this is the 8th problem. So 8th problem we have to find the limit x tends to a, x power lambda minus a power lambda by x minus a. This is also an important sum. So we want to prove that this is equal to lambda a power lambda minus 1. We want to show that limit is equal to lambda a power lambda minus 1. You can also show that using left hand limit and right hand limit, but these three sums are important, so that I am going theoretically. Now I am going to follow the same technique which I followed in the previous sum. I am going to take x is equal to a times 1 plus y. So I am replacing x to be a into 1 plus y. So this will be changed to a is a power lambda 1 plus y whole power lambda, because x is a into 1 plus y. So x power lambda will be a power lambda 1 plus y whole power lambda minus a power lambda is there. So I am changing x to be a times 1 plus y minus a. So a power lambda is common in the numerator, so I can take a power lambda outside. So I have 1 plus y whole power lambda minus 1. So I have, if I multiply here, a plus ay minus a. So this minus a and this plus a will get cancelled. So I have only ay. So I have here a. So I can, if I take a this to numerator, it will become, I can write this as a power lambda minus 1. So this is again as it is, 1 plus y whole power lambda minus 1 by y. Again we make a substitution. I am going to take this numerator full T to be z. So put 1 plus y whole power lambda minus 1 is equal to z. So 1 plus y whole power lambda will become, if I take 1 to this side, it will become 1 plus z. So I am taking log on both sides. So I have log 1 plus y whole power lambda is equal to log 1 plus z. I am applying the property that I can multiply the power, so that it will be lambda log 1 plus y is equal to log 1 plus z. So this now is changed to x power lambda minus a power lambda by x minus a is equal to this. And since I have taken this to be z, so this is equal to a power lambda minus 1 into z by y. Now I am multiply and divide by log 1 plus z. So I multiply by log 1 plus z and divide by 1 log 1 plus z, so that it will not affect the system. So I can write this z as, I am multiplying log 1 plus z numerator and the denominator. Now we know that log 1 plus z is lambda log 1 plus y. So I am replacing log 1 plus z to be lambda log 1 plus y. Now I can write this z to be 1 by z and this y to be 1 by, I can write this as 1 by y log 1 plus y, 1 by y. Now again I am applying the property that this I can write this as log 1 plus z whole power 1 by z, because this is equivalent to 1 by z log 1 plus z. So I can write this as lambda log 1 plus y whole power 1 by y, because if I apply the property, it will be changed to 1 by y log 1 plus y, which is equal to the previous step. So again 1 plus n whole power 1 by n is e. Again this is 1 plus n whole power 1 by n. So in place of n I have y here, here I have z. So this is changed to a power lambda minus 1 1 by log e lambda log e. So this will be changed to log e. This is again changed to log e. So as limit z tends to 0, 0, 0, this will be log e, this will be log e. So this and this will get cancelled. So I can take this lambda multiply this lambda outside. So I have lambda a power lambda minus 1. So this is the limit for this function. So we have successfully solved the problems based on limits. So from the next video we will going to solve the indeterminate forms. It will be very easy. If you know some basic differentiation formulas, we can able to tackle any problems in indeterminate form. So from next video it will be very interesting to solve the indeterminate forms. So these three will be slightly vague, so you need to thorough with these three sums. From the next video it will be very easy to solve the indeterminate forms. So we'll see the next video. Goodbye. Thank you.